So I'm going to go through this example problem, and then you will be doing the other problems that are on the assignment that is by the same name as this title. All right, and this diagram is shown on that sheet as well. You can use any method you want to show your work when you do those problems. So let's look at this. We're going to look at each frame of this little example. So if we have the spring alone, a vertical spring, and it's at rest, it is 0.3 meters long. Now, if you take a steel ball and you put it onto the spring, it compresses so that now, excuse me, now it is only 0.2 meters long. That steel ball has pushed on the spring. Now let's push the spring down a little harder with our hand, and so that the spring is now 0.1 meters. Well, now the force in the spring is greater than the weight of the steel ball, right? Because we've actually forced it down. In frame 2 here, I can put this frame 2. Frame 2, what happened is that the spring comes to rest when the force in the spring is equal to the weight of the ball, right? Notice the ball too I did not give you the mass. It's already in newtons. So we don't have to convert it to force. All right, so the first thing we have to do in this case is find out what the spring constant K is. That's the purpose of showing you number 2. So to find out the spring constant, we're going to use equation 15. Put right there. Equation 15, force in the spring is equal to K times X. Well, we know the force in the spring is 8 newtons, right? Remember, when we do these problems, we always write out the equation we're going to use, write down the variables with their units, and then plug in to the equation. That's the force in the spring. What is X? X is how far the spring is compressed. And the spring, when it's at rest, is at 0.3 meters. And when it's compressed, it's at 0.2 meters. So the compression is actually the difference between there. It's 0.1 meter, right? This is X right there. And we're going to try to find what K is. What is K? So we'll put these values in to the equation. And K is equal to, it should be a lowercase k. I'll just make it, there we go, is 80 newtons per meter. It takes 80 newtons to compress it a meter, and so it only takes 8 newtons to compress it 1/10 of a meter. That makes sense. All right, now we're going to push that ball down onto the spring, as shown in 3. That means that now there is some potential energy in that spring, and that energy can actually push the ball up a certain distance. How high will that ball go? Well, that potential energy is going to be converted from this potential energy in the spring to potential energy of gravity, or gravitational potential energy. An equation we can use is to describe this is number 22. In some ways, it's not perfect, but this is saying that the total energy as the object moves up is not going to change at all. So this is the total energy. Now we're going to this first one is potential energy. The PE is potential energy, and the second is kinetic energy, and Q is internal energy. That's if friction is involved. The particles of the ball itself would be heating up. That's internal energy. So there's the the energy that the particles have because of their position or because they're moving around together, or there's energy because of the particles themselves are moving around inside. Like if the ball heated up, that would be internal energy. And we can actually get internal energy to increase if we have friction, right? Because if you take your hands and you rub them together, what happens to your hands? They get warm. The internal energy of your hands are getting warm. But in this question, we're going to ignore that. We're not going to have any of that energy, internal energy. So we're going to look at two points. So if we were to look at this ball, I'm trying to think of how to draw this exactly. I'm going to redraw this. So point 1 will be the ball on the spring when it's compressed. All right, and then it's going to go up into the air, and it will be up here at some point, right? This is point 2. And we don't know what this distance is. That's what we want to know. You guys see that? Okay. Now, the total energy doesn't change from point 1 to point 2. And so what we can say is that the potential energy at point 1 plus the kinetic energy at point 1 equals the potential energy at point 2 plus the kinetic energy at point 2. That's how we use this equation. We haven't talked about kinetic energy, but kinetic energy is the energy of motion. And at both point 1 and point 2, the object's not moving at all. We're holding it steady at point 1. We let it go. It goes up in the air and it stops. We want to know how high it goes. So it's going to, the maximum height, it's stopped. It's stopped from going positive direction. It's about to go to the negative direction. So there is no kinetic energy at all. I can fortunately just erase it. That's pretty cool. So the potential energy equals the potential energy. Now, these are different types of potential energy, though, right? In the first, at 1, what is the potential energy? It's the potential energy in a spring. All right, so we should use that equation, which is equation 16 on your reference tables. All right. And what type of potential energy does it have when it's up in the air? Well, it's above the ground for some distance. So the potential energy when it's up in the air is simply this, equation 19. So because these are going to be, that is that, we can set these equal to each other. So we'll have 1/2 kx squared equals to mg delta h. Let's put our variables in there. We know that k, here maybe I should do this on the next page. I think I can. Oh, I know how to do it. Get rid of everything else. Just gonna move that there. Okay. So our K is 80 newtons per meter. Our X is, let's go back and look. Our X is now 0.2 because we compressed it down a little farther. Our mg, I'm going to say mg total, is 8 newtons. That's how heavy the ball is, right? We know that's our mng. And then our delta H. That's what we're looking for. We want to know how high the ball went. So we plug these values in. 1/2 80 x squared, 0.2 squared equals 8 times delta H. And can we solve for that? You can do this too, so you're checking me. I get 0.2 meters. Is that right? You guys get that? What's that? All right. So it doesn't actually get back to the equilibrium point, but it does get higher than when it's just resting. Wait, no, it doesn't. What was that? Oh, yes, you do. Yes, you're right. Right. So the delta H is that. So the total height is 0.2 plus 0.1. So it's 0.3 meters above the ground. Right. Because delta H was that right there. Okay. Homeroom time.